So in this video we're going to be looking at closed contour integrals, and in particular these two integrals over this contour. Now we've got this integral here, 1 over z dz over the contour gamma, and 1 over z to the power of n with respect to z over the contour of gamma, the same contour. This time n is greater than 1 and is a positive integer, so z squared, z cubed, etc. Now both of these will give us a different result, as you'll see in a moment, but they are really important results in terms of complex analysis and the residue theorem and finding the result of integrals using these values. So what have we got here? So our path here goes in a circle around the complex plane, and it starts from this point here. Now if we call the start point M on this path and the end point N, what we will get is that f of m equals f of n. So that's important first of all, because that then defines it as a closed path. So we must have that as our definition when we're using the integrals as well. Now also round here, the function that describes this circle must also be continuously differentiable everywhere. So we will also get this result, f prime of m equals f prime of n. Okay, now this point here is the only point where the function is repeated in its value, i.e. it's 1 to 1 everywhere except the start and end point. Okay, so now let's deal with these two integrals. Now the way to deal with that is our complex value here for z. What we'll do with that is we'll turn that into parameterization. So we'll now define z equals e to the it, where t goes from 0 to 2 pi as it traverses the circle anti-clockwise. But as our radius is defined as just the variable r, we also need a value r here. So that's almost our that is our polar form of our complex values. So now if we're going to use that into our integral, we need a dt. So we need to take the derivative of this with respect to t. So dz dt, that equals, well, we've got it, so we multiply by I, so IR e to the it. So that's our derivative with respect to t, and we need to define our t, as we said, is from 0 to 2 pi. So t goes from 0 to 2 pi. So in complex analysis, that defines our circle using this. Okay, so now we need to put this information into here. So now we have our integral across our contour, which goes from 0 to 2 pi in terms of parameterization. 1 over z, so we've got 1 over z is r e to the it. And then our dz now becomes I r e to the it dt. So r e to the it dt. So that takes care of that. I'm not forgetting our I as well. So we've got 1 times that. Okay, now what can we do now? Well, there's a lot of simplification we can do there. We've got e to the it numerator and denominator. So there you go. We've got our r for our radius in numerator and denominator. There you go. So we're just left with 1 times I, which gives us I. So that leaves us a nice integral to be dealing with. The integral of I with respect to t. So that just gives us it calculated from 0 to 2 pi. So let's take care of that. So 0 to 2 pi. Now, when t is 2 pi, we've got 2 pi I. So we've got 2 pi I. And when t is 0, we've just got 0. So that then becomes our result of this integral here. So equals 2 pi I. So let's write that up there. So that's that taken care of. Now let's have a look at this integral here. Okay, so we can use this information in here and use it as our parameterization substitution into here. So let's take care of that. Let's just put a line through this one. And now we've got the integral from 0 to 2 pi, 1 over z to the n. Now we've got to raise this to the power of n. So we'll have r to the n, e to the I, n t. So we've got r to the n, e to the I, n t. And our dz dt will be the same. So ir e to the it I r e to the I t dt. So that takes care of that. So now what can we do? Well, the simplification this time is not going to go quite as easily, so we need to just be a little bit careful on this one. So let's write our integrand sign there, 0 to 2 pi. That's not going to change. Now here, got I r and r to the n. So the I we can bring out, that's fine. Now the r and r to the n we can also bring out. Now here we've basically got r to the power of 1, and here we've got r to the power of n. So now, just without putting it as a fraction, we can write that as r to the 1 minus n. So r to the 1 minus n. So that would take care of the r values, and they can come outside of the integral because we're integrating with respect to t. Now here we've got e to the int, e to the it, so they will stay inside the integrand and be with respect to t. So what have we got here? So we've got basically 0n, and we've got e to the int. So we've got basically here I to the t, I to the nt. So then that will become e to the it. So we've got 1 minus n and an I included. So the I 1 minus n and then multiplied by t. So that would take care of all of that. Okay, now we can integrate this. So we've got I r to the 1 minus n. Now we need to divide by what we've got inside here as our multiple of our t. So it's I to the 1 minus n. So we divide by that, I 1 minus n. And then here, this input here will simply stay as it is. So we've got e to the I 1 minus n t. And that's all calculated from 0 to 2 pi. Okay, so what have we got here? So all of this not included in our value of t. So we've got I r to the 1 minus n over I 1 minus n. Now we can see these i's will cancel out, so there you go. And then we've got this one here, e to the I 1 minus n times 2 pi, when we've got t is 2 pi. So e to the I 1 minus n 2 pi. And then minus, now what we can do here, we can put this in a bracket and multiply all of it by this. So multiply when now t is 0. E to the I 1 minus n times 0. And let's see what that will give us. So e to the I, whatever value n is, as it's an integer, that will be I 2 pi, or I 4 pi, or I minus 2 pi. So now we've got r to the 1 minus n over 1 minus n, and then we've got 1. Then what happens here, when we've got e to the 0, we've got also 1. So now we've got this case here where this multiple here is multiplied by 0, so that is always going to give us 0. So therefore the result of this integral, regardless of the value of n, is always going to give us 0. So that's also another very useful result in terms of complex integrals and the residue theorem. Okay.